What if I told you that right now, as you're watching this video, you're experiencing a force that might not need mass to exist at all? In fact, what I'm about to show you will completely demolish everything you thought you knew about gravity. Here's the kicker. Einstein proved over a century ago that gravity isn't even a force in the traditional sense. And the most shocking part? Light, which has zero mass, creates gravity. Yes, you heard that right. Massless light bends spacetime. Now, before your brain completely melts, let me take you on a journey that will fundamentally change how you see the universe. By the end of this video, you'll understand why some of the smartest physicists alive today are questioning whether mass is even necessary for gravity to exist, and why this question might be the key to understanding the nature of reality itself. Here's what's going to blow your mind. There are objects in the universe right now, theoretical constructs called Kugelblitz, that are black holes made entirely of light. No mass, just pure energy creating such intense gravity that not even light can escape. And that's just the beginning. But before we dive into the deep end, I need you to do something for me. If you're ready to have your mind expanded in ways you never thought possible, hit that like button right now. And subscribe, because this journey requires commitment. We're about to spend the next few hours together unraveling one of the deepest mysteries in physics. Also, drop a comment right now telling me what country you're watching from and what time it is where you are. I want to know where in the world people are brave enough to question the fundamental nature of reality. Are you watching this at 2 a.m. like I would be? Let me know. Now, let's start with what you think you know about gravity. And then I'm going to systematically dismantle every assumption you've ever made. You learned in school that gravity is the force of attraction between masses. The more massive something is, the stronger its gravitational pull. Newton told us that, and for centuries, it worked perfectly. We could predict planetary orbits, calculate trajectories, and understand why we stick to the Earth. Simple, right? Mass attracts mass. End of story. Except it's not the end of the story. It's not even close. In 1915, a patent clerk turned physicist named Albert Einstein published his general theory of relativity, and everything changed. Einstein didn't just refine Newton's ideas. He completely revolutionized them. He told us something so radical that even today, over 100 years later, most people don't fully grasp its implications. Gravity is not a force between masses. Gravity is the curvature of space-time itself. Think of it like this. Imagine space-time as a massive rubber sheet stretched out flat. Now, when you place a bowling ball on that sheet, it creates a dip, a curvature. If you roll a marble near that dip, it will curve toward the bowling ball, not because the bowling ball is pulling it with some invisible force, but because the sheet itself is curved. The marble is simply following the geometry of the curved space. That's gravity. Objects don't pull on each other. They curve space-time, and other objects follow that curvature. But here's where it gets interesting, and this is crucial. Einstein's equations don't say mass curves space-time. They say energy and momentum curve space-time. Mass is just one form of energy. In Einstein's famous equation, E equals mc, mass and energy are equivalent. They're two sides of the same coin. This is the crack in the foundation that we're going to exploit. If energy curves spacetime and gravity is just curved spacetime, then anything with energy should create gravity, not just things with mass. And here's the revelation that should be dawning on you right now. Light has energy. Lots of it, but light has zero rest mass. Photons, the particles of light, are massless. Yet according to Einstein's equations, light must create gravity. Do you see what's happening here? We've just found our first piece of evidence that gravity can exist without mass. But I know what you're thinking. Sure, light has energy, so technically it can create a tiny amount of gravity, but it's negligible, right? It's the mass that really matters. Wrong, dead wrong. and I'm about to prove it to you. Let me introduce you to one of the most brilliant physicists of the 20th century, John Wheeler. Wheeler was Einstein's intellectual successor, a man who could think about physics in ways that bordered on the mystical. In 1955, Wheeler and his colleagues were exploring the implications of Einstein's equations when they stumbled upon something extraordinary. They were asking a simple question. If light can create gravity because it has energy, what happens if you concentrate enough light energy in one place? And they did the math. The equations led them to an inescapable conclusion. If you focus enough electromagnetic radiation, enough pure light energy, into a small enough region of space, the space-time curvature becomes so extreme that you create a black hole. A black hole made entirely of light. No mass required. They called it a Kugelblitz, German for ball lightning. It's a theoretical object, but it's not science fiction. It emerges directly from Einstein's equations, the same equations that have been verified thousands of times through observation and experiment. Think about what this means. A Kugelblitz is gravity in its purest form, divorced entirely from mass. It's the ultimate proof that the answer to our question, can gravity exist without mass, is a resounding yes. But Kugelblitz are just the beginning. The rabbit hole goes so much deeper, and every layer reveals something more profound about the nature of reality. Now, I want you to pause for a moment and really let this sink in. Everything you thought you knew about gravity, everything you were taught in school, was fundamentally incomplete. Gravity isn't about mass attracting mass. It's about energy and momentum, curving the fabric of space-time itself. Mass just happens to be a really efficient way of packing energy into a small space, but it's not the only way. And here's the thing that should be sending shivers down your spine. If gravity doesn't require mass, then what is mass really? Why do some particles have it and others don't? And more importantly, what does this tell us about the fundamental structure of the universe? Over the next several hours, we're going to explore these questions in depth. We're going to look at the mathematics, the experiments, the cutting-edge theories that are pushing physics into territory that would have seemed like pure fantasy just decades ago. We're going to meet the scientists who are grappling with these ideas right now, in real laboratories and in the abstract spaces of theoretical physics. But first, we need to build a solid foundation. We need to really understand what Einstein discovered, what his equations actually say, and why they lead to conclusions that seem so counterintuitive. Because here's the secret. Once you truly understand Einstein's insight, the idea that gravity can exist without mass isn't just possible, it's inevitable. So let's go back to 1915, to the moment when Einstein completed his general theory of relativity. He had been working on this for nearly a decade, struggling with the mathematics, collaborating with his friend Marcel Grossmann, who helped him learn the advanced geometry he needed. And when he finally arrived at his field equations, the equations that describe how matter and energy curve spacetime, he realized he had done something profound. The equations are beautiful in their simplicity, at least conceptually. On one side of the equation, you have the curvature of spacetime, described by something called the Einstein tensor. On the other side, you have the stress-energy tensor, which describes the distribution of matter and energy. Here's the exact formulation. G equals 8gc times t. Don't let the notation intimidate you. What this says is simple. The geometry of spacetime on the left equals the distribution of energy and momentum on the right, with some constants thrown in to make the units work out. But look at that right side. It's the stress-energy tensor, T. It doesn't just include mass. It includes all forms of energy. Kinetic energy, potential energy, pressure, momentum flux, electromagnetic energy, everything. Mass is just one contributor, and it's not even always the dominant one. In regions of intense electromagnetic fields, the energy in the field itself can contribute significantly to spacetime curvature. In the early universe, radiation dominated over matter, and the expansion of space was driven primarily by the gravity of massless photons. This is not speculation. This is established physics, confirmed by observations of the cosmic microwave background radiation, the afterglow of the Big Bang. We can see the gravitational effects of radiation in the early universe. We can measure it. So when we ask, can gravity exist without mass? We're not asking a hypothetical question. We're asking about something that definitely happened in the real history of our universe. Gravity existed and was enormously important at times when mass was barely relevant. But let's make this even more concrete. Let me give you another example that might surprise you. Have you ever heard of gravitational waves? In 2015, the LIGO Observatory made history by detecting gravitational waves for the first time, confirming a prediction Einstein made exactly a century earlier. Kip Thorne, one of the physicists who founded LIGO, had spent his entire career working toward this moment. When the detection was announced in February 2016, it was front-page news around the world. But here's what's fascinating. Gravitational waves themselves are ripples in spacetime, and these ripples carry energy. They can do work. If you had two objects floating in space and a gravitational wave passed through, it would cause those objects to oscillate, moving them back and forth. That motion requires energy, so gravitational waves have energy. And remember, anything with energy curves spacetime, which means gravitational waves create gravity. Gravity creates more gravity, and gravitational waves have no mass. They're pure geometry, pure curvature, propagating through spacetime at the speed of light. Yet they gravitationally interact with matter and with each other. In regions of extremely strong gravitational waves, the nonlinear effects become important. The waves can focus and interact in ways that create even more curvature. Theoretically, you could have a configuration of gravitational waves so intense that they collapse into a black hole, a phenomenon similar to the Kugelblitz, but even more abstract. A black hole made of gravitational waves, made of pure space-time curvature, with no matter or electromagnetic energy at all. Are you starting to see the pattern? Every time we look deeper into Einstein's equations, we find more examples of gravity without mass. It's not an exotic edge case. It's woven into the fundamental structure of general relativity. Now, let me address something that might be bothering you. You might be thinking, okay, but even if light and gravitational waves can technically create gravity, it's so weak that it doesn't matter, right? Real gravity, the kind that holds galaxies together and keeps us on Earth, that comes from mass. And you'd be partially right. In our everyday experience, and in most astrophysical situations, mass is indeed the dominant source of gravity. The gravity of the Earth, the Sun, black holes as we normally think of them, these are all dominated by mass. But here's the thing. The fact that mass dominates in most situations is an accident of the conditions in our universe. It's not a fundamental requirement. In different conditions, energy without mass can be just as important, or even more important. And more intriguingly, there are theoretical scenarios, some of them connected to cutting-edge physics beyond general relativity, where massless gravity becomes not just possible, but essential. This is where things start to get really wild, and this is where we need to start talking about the frontier of modern physics. Because the question, can gravity exist without mass, isn't just an abstract curiosity. It's directly related to some of the deepest unsolved problems in physics: the nature of dark energy, the possibility of quantum gravity, and even the fundamental question of why mass exists at all. Let me leave you with this thought as we transition to the next phase of our journey. In 2012, physicists at CERN announced the discovery of the Higgs boson, the particle responsible for giving other particles mass. Peter Higgs and Francois Englert won the Nobel Prize for predicting this particle back in 1964. But here's what's profound. The Higgs mechanism doesn't give mass to photons. Photons remain massless. Yet photons interact with the Higgs field in subtle ways. And the Higgs field itself has energy, which means it curves space-time and creates gravity. So we have a field whose job is to create mass, but which itself creates gravity through its energy, not through mass. And the particles that carry this field, Higgs bosons, have mass, but that mass comes from the energy of the field configuration, not from any intrinsic property. It's turtles all the way down, except it's not turtles. It's energy. Energy curving space-time, creating what we perceive as gravity. And mass is just along for the ride. Now, before we go deeper, I want you to take a moment and really appreciate where we are. We've established that gravity doesn't require mass. We've seen multiple examples. Light creating gravity, gravitational waves creating gravity, even purely theoretical constructs like Kugelblitz. We've traced this back to Einstein's fundamental equations, which make it clear that energy, not mass, is what curves spacetime. But we're just getting started. What I want to do now is take you deeper into the implications of this. Because once you understand that gravity can exist without mass, a whole cascade of questions opens up. Questions about the nature of space and time, about quantum mechanics, about the origin and fate of the universe. And some of these questions lead to answers that are so strange, so far outside everyday experience, that you might think we've left science behind and entered the realm of philosophy or even mysticism. But I promise you, everything I'm going to tell you is grounded in rigorous mathematics and, where possible, in experimental evidence. The universe is stranger than you think. It's stranger than you can think. And the strangeness starts with something as simple as asking whether gravity needs mass. Are you ready to go deeper? Because there's no turning back from here. Once you see what I'm about to show you, you'll never look at the universe the same way again. Let's talk about vacuum energy and why empty space might be the most massive thing in the universe. And yes, I'm aware of the paradox in that statement. That's exactly the point. You think of empty space as nothing, right? A void, an absence of everything. But according to quantum mechanics, empty space is anything but empty. It's seething with activity, filled with what we call quantum fluctuations or virtual particles. These are particle-antiparticle pairs that pop into existence for the briefest instant allowed by Heisenberg's uncertainty principle, then annihilate each other and disappear. Now, here's where it gets weird. These fluctuations have energy. They must, because energy is required to create particles, even virtual ones, and we can measure this energy. It shows up in experiments like the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. The Casimir effect is simple in concept, but profound in implications. Take two uncharged metal plates and place them extremely close together in a vacuum. Quantum theory predicts that the vacuum fluctuations between the plates will be different from the fluctuations outside the plates, because the plates restrict which wavelengths of virtual photons can exist between them. This creates a pressure difference, and the plates are pushed together by a measurable force. And we've measured it multiple times in ever more precise experiments. The Casimir force is real. The vacuum has energy. But here's the trillion-dollar question. If the vacuum has energy, and energy curves space-time, then the vacuum should create gravity. Empty space should have weight. The absence of everything should pull on things. And according to our best calculations, it does. We call it vacuum energy or dark energy, and it's the biggest mystery in cosmology right now. In 1998, two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, made a discovery that shocked the physics community. They were studying distant supernovae, trying to measure how the expansion of the universe was slowing down due to gravity. And what they found was the opposite. The expansion is speeding up. Something is pushing the universe apart, and we call it dark energy. Perlmutter, Schmidt, and Rees won the Nobel Prize in 2011 for this discovery. The best explanation we have for dark energy is that it's the energy of empty space itself, the quantum vacuum energy. And here's the kicker. This energy has no mass. It's not made of particles. It's a property of spacetime itself. Yet it creates gravity, a repulsive form of gravity that's accelerating the expansion of the universe. So not only can gravity exist without mass, but the dominant gravitational effect in the universe right now, the thing that's determining the fate of all existence, is gravity from massless vacuum energy. Let that sink in for a moment. The most important gravitational phenomenon in the universe has nothing to do with mass. But wait, it gets even weirder. Because when we try to calculate how much vacuum energy there should be based on quantum mechanics, we get an answer that's wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. Our theory says the vacuum energy should be enormous, so large that the universe should have torn itself apart instantly at the moment of the Big Bang. But observations tell us the vacuum energy is tiny, just barely enough to account for the observed acceleration of cosmic expansion. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. And at its heart, it's a question about massless gravity. Why is the gravity of empty space so much weaker than it should be? Nobody knows. We have proposals, speculative ideas involving extra dimensions, quantum gravity, anthropic reasoning, but no definitive answer. The universe is telling us something fundamental about the relationship between quantum mechanics, space-time, and gravity, and we haven't figured out what it is yet. But here's what we do know. Dark energy is real, it's massless, and it's gravitationally important. It makes up about 68% of the energy content of the universe. Dark matter, which probably does have mass, though we haven't detected it directly, makes up about 27%. And normal matter, the stuff you're made of, the Earth, the Sun, all the stars and planets we can see, that's about 5%. The universe is dominated by things that either have no mass, dark energy, or whose mass we don't understand, dark matter. The gravity that shapes the cosmos is mostly not coming from what we think of as normal mass. This is the reality we live in. Gravity without mass isn't some exotic theoretical curiosity. It's the dominant theme of our universe. Now, let me take you even deeper, because we need to talk about what happens when we try to combine general relativity with quantum mechanics, and why that leads us to even more radical conclusions about the nature of gravity and mass. Einstein's general relativity is a classical theory. It treats space-time as smooth and continuous, a fabric that can be curved but not torn or broken. Quantum mechanics, on the other hand, tells us that everything comes in discrete chunks, quanta. Light comes in photons. Electrons have discrete energy levels. Even space itself might be quantized at the smallest scales. So what happens when we try to describe gravity quantum mechanically? What would a quantum theory of gravity look like? This is the holy grail of theoretical physics, and we don't have a complete answer yet. But we have strong candidates, and they tell us something remarkable about gravity and mass. The most developed candidate is string theory, though I should mention it's controversial and unproven. But let's talk about what it says, because it's illuminating. In string theory, the fundamental constituents of reality aren't point particles, but tiny, vibrating strings of energy. Different vibration patterns correspond to different particles. An electron is a string vibrating one way, a quark is a string vibrating another way, and so on. And here's the crucial part. The graviton, the hypothetical quantum particle that carries the gravitational force, is just another vibration mode of the string. Gravity isn't something separate from the other forces. It's another note in the symphony of vibrating strings. But strings themselves have no mass in the usual sense. Mass emerges from how the strings vibrate and interact. A string vibrating in a low-energy mode appears as a massless particle, like a photon. A string in a high-energy mode appears massive. So in string theory, mass isn't fundamental, it's derived. It's an emergent property of more basic entities, strings, that don't themselves have mass. And gravity? Gravity is just the way these strings interact through their vibrations. The graviton is a massless particle, traveling at the speed of light, mediating gravitational interactions. The picture that emerges is radical. At the deepest level, there is no mass. There are only energy patterns, vibrations, and the spacetime that emerges from their interactions. Gravity is a consequence of these patterns, and mass is just a particular type of energy configuration. Now, string theory might be wrong. We don't know yet. But similar conclusions emerge from other approaches to quantum gravity, like loop quantum gravity or causal set theory. In almost every attempt to quantize gravity, mass becomes less fundamental, more derived, more emergent. The trend is clear. The more deeply we probe the foundations of physics, the more gravity and mass separate. Gravity becomes fundamental, while mass becomes derivative. So can gravity exist without mass? Not only can it, but at the deepest level, gravity might be all there is, and mass might just be a useful fiction we invented to describe certain patterns of gravitational interaction. Let me give you an analogy. Think of it like this. Imagine you're watching waves on the ocean. You see crests and troughs, patterns moving across the surface. Now, you might point to a particularly large wave and say, that wave has mass. It's carrying momentum and energy. But the wave doesn't really exist as a thing. It's just a pattern in the water. The water molecules are moving up and down, but they're not traveling with the wave. The wave is a configuration, a shape, not an object. Mass might be like that. It might be a pattern, a configuration of fields and energy moving through spacetime. The spacetime curvature is real. The energy is real. But mass? Mass might just be a convenient label for a particular type of pattern. And gravity? Gravity is just the fundamental response of spacetime to any form of energy, whether that energy is configured into what we call mass or not. This is a profound shift in perspective. We're used to thinking of mass as the primary thing and gravity as its consequence. But physics is increasingly suggesting the opposite. Gravity is primary, and mass is the consequence. Now, I want to pause here and make sure you're still with me, because we've covered a lot of ground. We started with the simple question of whether gravity can exist without mass. We've seen that it can, in multiple ways. Through electromagnetic energy, through gravitational waves, through vacuum energy. We've explored how general relativity makes this not just possible, but inevitable. And we ventured into quantum gravity and string theory, where mass itself becomes questionable as a fundamental concept. But there's another dimension to this question that we haven't explored yet, and it's going to take us into even stranger territory. We need to talk about the relationship between gravity and information, and why some physicists think gravity might be an emergent phenomenon, not a fundamental force at all. This is where things get truly mind-bending. So take a deep breath, maybe pause the video and grab a coffee, because we're about to venture into ideas that challenge not just our understanding of gravity and mass, but our understanding of what reality is. And before we continue, if you're still here, if you've made it this far into this journey, you're part of a select group. Most people would have clicked away by now. The fact that you're still watching tells me you're genuinely curious about the deep structure of reality. That's rare and valuable. So do me a favor, hit that like button if you haven't already, and subscribe so you don't miss the next deep dive. And seriously, drop a comment telling me where you are and what time it is. I want to know who my fellow reality explorers are. All right, let's talk about the holographic principle and why it suggests that gravity might not be fundamental at all. In the 1970s, a physicist named Jacob Bekenstein made a strange discovery about black holes. He was studying the thermodynamics of black holes, trying to understand them as physical systems that have temperature and entropy. And he found something bizarre. The entropy of a black hole, which measures how much information it contains, is proportional not to its volume, but to the area of its event horizon. This was weird because for normal objects, entropy depends on volume. A bigger box can contain more information than a smaller box. But black holes are different. All the information about what fell into a black hole is somehow encoded on its two-dimensional surface, not in its three-dimensional interior. Stephen Hawking built on Bekenstein's work and showed that black holes emit radiation, now called Hawking radiation, and this radiation carries information. This led to a radical proposal called the holographic principle, developed further by Gerard T. Hooft and Leonard Susskind in the 1990s. The holographic principle says that all the information contained in a volume of space can be encoded on the boundary of that region, like a hologram. Think of it like this. A hologram is a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests that our entire universe might be like that, a three-dimensional image projected from information encoded on a two-dimensional surface. And here's where it connects to gravity. In the holographic picture, gravity isn't a fundamental force. It's an emergent phenomenon arising from the way information is organized on the holographic boundary. This idea was developed most fully by Erik Verlinde, a Dutch physicist who in 2010 proposed what he called entropic gravity. Verlinde's idea is that gravity is not a fundamental force, but an emergent phenomenon, similar to how temperature emerges from the collective motion of atoms. When you heat a gas, the temperature rises. But temperature isn't a fundamental property of individual atoms. It's a statistical property of the ensemble. Verlinde suggested that gravity works the same way. It emerges from changes in information entropy when particles move. In Verlinde's picture, spacetime is fundamentally informational. It's made of bits, quantum units of information. When mass energy is present, it changes how these bits are organized, and that reorganization creates what we perceive as gravitational attraction. The key point is this. In entropic gravity, the gravitational interaction doesn't require mass. It requires information. Mass is just one way of encoding information, but there are others. Any configuration that changes the entropy of spacetime will create what looks like a gravitational effect. Now, I have to be clear. Entropic gravity is speculative. It's not proven, and many physicists are skeptical. But it's a serious research program, and it makes testable predictions. Some of those predictions match observations better than standard gravity theories, particularly regarding the behavior of galaxies. Whether or not Verlinde is exactly right, the holographic principle itself is on very firm ground. It emerges naturally from string theory and black hole thermodynamics. And it strongly suggests that our usual way of thinking about gravity as a force between masses in three-dimensional space is missing something fundamental. The universe might be holographic. Gravity might be emergent. Mass might be a particular way of organizing information. And at the deepest level, reality might be made of bits, quantum information, with everything else space, time, matter, force emerging from how those bits are arranged. Do you see how far we've come? We started by asking whether gravity can exist without mass, and we've ended up questioning whether either gravity or mass are fundamental at all. They might both be emergent, arising from something deeper, the quantum information structure of spacetime itself. This is the frontier of physics right now. This is where the smartest people in the world are pushing, trying to understand what reality really is at its deepest level. And here's what I want you to understand. This isn't just abstract theorizing. These ideas have consequences. They change how we think about black holes, about the Big Bang, about the ultimate fate of the universe. They might even connect to practical technologies, quantum computers, for instance, which manipulate quantum information directly. We live at a unique moment in history. For the first time, we have the mathematical tools and experimental capabilities to probe the fundamental nature of reality. The answers we're finding are stranger than anyone expected. Gravity without mass is just the beginning. Now, let me bring this back to something more tangible, because I want you to see that these abstract ideas connect to real physics, real experiments, real observations we can make. Let's talk about how we might actually test whether gravity can exist without mass. Because that's the ultimate test of any physical theory. Can we observe it? Can we measure it? Can we rule it in or out? One of the most promising avenues involves something called frame dragging. This is a prediction of general relativity that's been confirmed by experiment, and it directly shows how energy without mass can create gravitational effects. Frame dragging is the idea that a rotating object drags space-time around with it as it spins. Imagine space-time as a fluid, and a rotating planet as a ball spinning in that fluid. The fluid near the ball gets dragged along with the spin. In 2004, NASA launched a satellite called Gravity Probe B, designed specifically to measure frame dragging around Earth. The satellite contained 4 ultra-precise gyroscopes, and the experiment looked at how the orientation of these gyroscopes changed as they orbited Earth. According to general relativity, Earth's rotation should drag space-time around with it, and this should cause the gyroscope's depresses to slowly change their orientation in a specific way. And that's exactly what was observed when the results were announced in 2011. But here's the interesting part. Frame dragging isn't caused by mass alone. It's caused by angular momentum, which is mass times velocity. The velocity part contributes independently. In principle, you could have frame dragging from rotating electromagnetic fields, from rotating light, from anything with angular momentum mass not required. We haven't yet created a configuration with enough electromagnetic angular momentum to measure its frame dragging effect, but theoretically, it should exist. A sufficiently intense, rotating laser beam should drag space-time around with it, creating measurable gravitational effects with no mass involved. This is testable. Difficult, but testable. And experiments are being designed right now to look for exactly this kind of effect in extreme electromagnetic environments, like those around pulsars or in plasma physics laboratories. Another testing ground is gravitational lensing. When light passes near a massive object, its path bends due to the curvature of spacetime. This is called gravitational lensing, and it's one of the most spectacular confirmations of general relativity. We can see distant galaxies distorted into arcs and rings by the gravity of intervening galaxy clusters. But gravitational lensing doesn't just reveal the mass of the lensing object. It reveals its total energy content, including dark energy and any other forms of energy that contribute to spacetime curvature. Some of the most detailed studies of gravitational lensing have found anomalies, small discrepancies between what we expect from the visible and dark matter and what we actually observe. Some researchers have suggested these might be signatures of massless contributions to gravity vacuum energy fluctuations, quantum effects, or other exotic sources of spacetime curvature. These are tentative findings, and there are other possible explanations. But they show that we're actively looking for signs of gravity without mass, and we have the tools to find them if they're there. There's also the cosmic microwave background, the CMB, which is the oldest light in the universe, emitted about 380,000 years after the Big Bang. The pattern of fluctuations in the CMB contains an enormous amount of information about the early universe, and we can extract details about what kinds of energy were present and how they affected the evolution of cosmic structure. The CMB data from satellites like WMAP and Planck has revolutionized cosmology. And one thing it tells us clearly is that radiation massless photons was gravitationally important in the early universe. We can see its gravitational effects directly in the CMB fluctuations. So we've already measured gravity from massless energy. It's not speculation. It's confirmed observational fact. The frontier now is looking for more exotic forms. Can we detect the gravitational effect of quantum vacuum fluctuations? Of dark energy variations? Of quantum entanglement, which some theories suggest might contribute to spacetime structure? These are questions being pursued right now in laboratories and observatories around the world. The technology is improving rapidly. Gravitational wave detectors like LIGO are getting more sensitive. New space telescopes are being launched. Quantum sensors are becoming available that can measure gravity with unprecedented precision. Within our lifetimes, we might directly detect gravitational effects that have no classical mass source. We might see Kugelblitz forming in the early universe or in exotic astrophysical environments. We might measure the gravitational interaction of light beams in high-intensity laser facilities. The point is, this is real physics. It's not just mathematical speculation. We're at the stage where theory and experiment are starting to converge on the question of gravity without mass, and the answer is becoming clear. Yes, it exists, and yes, we can measure it. But beyond the experimental questions, there's a deeper philosophical issue that I want to address, because it's crucial for understanding what this all means. When we ask, can gravity exist without mass? We're really asking about the fundamental building blocks of reality. What are the truly basic, irreducible elements from which everything else is constructed? For a long time, we thought mass was one of those basic elements. Matter was fundamental. The universe was made of stuff, and that stuff had mass, and mass created gravity. But every advance in physics has moved us away from that picture. First, we learned that matter is made of atoms. Then, that atoms are made of electrons and nuclei. Then, that nuclei are made of protons and neutrons. Then, that protons and neutrons are made of quarks and gluons. At each level, what seemed solid and fundamental turned out to be composite, made of smaller, more fundamental things. And now, we're realizing that even quarks and electrons might not be truly fundamental. They might be vibrations of strings, or knots in quantum fields, or patterns in some more abstract mathematical structure. Mass, in this picture, is not fundamental. It's derived emergent, a property that appears only at higher levels of organization. What is fundamental, as far as we can tell, is energy and information. The universe, at its deepest level, might be nothing but patterns of energy and information, evolving according to mathematical laws. Gravity, in this view, is not a force between masses, but a consequence of how energy and information shape spacetime. Mass is just one particular configuration of energy, common in our universe, but not essential to the existence of gravity. This is a profound shift in worldview. It means that the solid, material world we experience is in some sense an illusion, or at least a very high-level emergent description of something much more abstract underneath. Does this make the world less real? No. The table in front of you is still solid. The ground still holds you up. The stars still shine. But the ultimate nature of these things is not what it seems. Solidity is a pattern. Mass is a pattern. Even gravity, in some sense, is a pattern in the geometry of spacetime itself. And here's where this becomes personally relevant, where it connects to your life and your understanding of yourself and the universe you inhabit. You are made of atoms. Those atoms are made of particles. Those particles have mass. But that mass emerges from the energy of quantum fields, from the vibrations of quarks bound together by gluons, from the Higgs field giving particles their inertia. At your most fundamental level, you are not made of matter. You are made of energy, organized in very specific, very complex patterns. The gravity that keeps you on Earth, that holds the atoms of your body together, that prevents you from flying apart, it's not responding to your mass in some ultimate sense. It's responding to your energy, to the information encoded in the patterns that make you you. And here's something that should blow your mind. The vast majority of your mass doesn't come from the particles themselves. Protons and neutrons are made of 3 quarks each, but the quarks account for only about 1% of the proton's mass. The other 99% comes from the binding energy of the strong force holding the quarks together. You are made of energy pretending to be matter. Your mass is mostly borrowed from force fields, and gravity responds to all of it equally: the particle masses, the field energies, the binding energies, everything. You are a walking, thinking proof that gravity doesn't need mass in the traditional sense. You are an emergent pattern of energy, and gravity is the universe's response to that pattern. Now, let me take this even further, because we need to talk about consciousness and observation and how they might relate to this picture of reality as information and energy. This is going to sound wild, but bear with me. In quantum mechanics, the act of observation plays a crucial role. Before you measure a quantum system, it exists in a superposition of multiple states. The electron is in many places at once. The photon takes all paths simultaneously. But when you observe it, when you interact with it in a way that extracts information, the superposition collapses and you get a definite outcome. This has led to deep philosophical debates about the role of consciousness in physics. Some physicists, like Eugene Wigner, suggested that consciousness might be fundamental to the quantum measurement process. Others, like Hugh Everett, proposed a many-worlds interpretation where all outcomes occur, but in different branches of reality. Now, here's where it connects to gravity. If the universe is fundamentally informational, if space-time and gravity emerge from quantum information, then observer systems that process and record information might play a deeper role than we thought. Some researchers have proposed that consciousness itself might be a kind of information processing that's deeply connected to the structure of space-time. Roger Penrose and Stuart Hameroff have suggested that quantum gravity effects in the brain might be relevant to consciousness, though this remains highly controversial. But leave aside the specific mechanism. The point is this: if gravity emerges from information, and if consciousness is fundamentally about information processing, then there might be a deep connection between the two. You, as a conscious being, are not just a passive observer of gravity. You are a complex information processing system embedded in spacetime, extracting information from your environment, making decisions, acting on the world. In doing so, you're participating in the very processes that give rise to spacetime structure. This sounds mystical, but it's actually grounded in physics. Every time you observe something, you're extracting information from the quantum state of the universe. That information extraction has physical consequences. It changes entropy. It changes the distribution of quantum correlations. And if gravity emerges from information, then it changes gravity too. The effect is unimaginably tiny for any single observation. But across the entire universe, across all observers and information processing systems, these effects might add up to something significant. Some physicists have even speculated that the act of observation itself might contribute to dark energy, to the acceleration of cosmic expansion. When you observe the universe, you extract information, you increase entropy, and that entropy increase might manifest as a kind of repulsive gravitational effect. This is extremely speculative, and I want to be clear about that. But it's not crackpot speculation. It's based on legitimate attempts to connect quantum information theory with cosmology and gravity. The point I'm making is this: once you understand that gravity can exist without mass, once you see that gravity emerges from energy and information, the door opens to all kinds of possibilities. Consciousness, observation, information processing, these might not be separate from physics. They might be fundamental aspects of how the universe works. You are not separate from the universe. You are the universe observing itself, processing information about itself, curving spacetime through your very existence and awareness. Now, I want to pivot and talk about the practical implications of all this, because understanding that gravity can exist without mass isn't just philosophically interesting, it might be technologically important. Consider Kogelblitz again, those theoretical black holes made of concentrated light. They're not just mathematical curiosities. Some physicists have seriously proposed using them as energy sources, or even as engines for spacecraft. The idea is this: if you could create a Kugelblitz, you could feed matter into it, and the matter would be converted to Hawking radiation as it evaporates. For very small Kugelblitz, the Hawking radiation would be intense and high energy. You could potentially extract enormous amounts of energy from a miniature black hole powered by light. In 2009, physicist Louis Crane and his colleague Sean Westmoreland published a paper exploring the feasibility of using Kugelblitz for spacecraft propulsion. They calculated that a Kugelblitz with a mass equivalent to about 1,000 tons could produce enough thrust to accelerate a spacecraft to a significant fraction of the speed of light. The technology to create Kugelblitz doesn't exist yet. We'd need lasers far more powerful than anything we currently have, but it's not violating any laws of physics. It's theoretically possible. And here's the amazing part: such an engine would be powered by gravity without mass. The thrust would come from Hawking radiation emitted by a black hole created from pure electromagnetic energy. No matter required, just concentrated light creating space-time curvature so extreme that it traps even light itself. This is the kind of thing that might be possible once we fully understand and can manipulate gravity at the fundamental level. There are other possibilities too. If we can generate strong gravitational effects using electromagnetic fields or other forms of energy, we might be able to create artificial gravity for spacecraft or space stations without rotation. We might be able to shield against gravity or focus it like a lens focuses light. Some of these ideas venture into what's currently science fiction. But so did lasers, quantum computers, and gravitational wave detectors, all of which are now reality. The line between science fiction and future science is often just a matter of time and engineering. Understanding gravity without mass opens doors. It expands the possibility space. It shows us that the universe is more flexible, more manipulable than we thought. And beyond the technological implications, there are cosmological ones. The question of gravity without mass directly relates to the biggest questions we can ask. Why does the universe exist? Why these laws of physics and not others? What happened before the Big Bang? And what will happen in the far future? Let me talk about the Big Bang, because this is where gravity without mass becomes absolutely critical. In the very early universe, in the first tiny fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Matter as we know it didn't exist yet. There were no atoms, no protons, not even quarks. Just pure energy, a seething plasma of quantum fields at enormous temperatures. In this environment, mass was irrelevant. Particles moved at nearly the speed of light. The distinction between massive and massless particles didn't matter much. Everything was highly relativistic. But gravity was extremely important. The expansion of the universe, the evolution of its structure, everything depended on gravity. And that gravity was driven almost entirely by radiation, by photons and other massless or nearly massless particles. We can see the effects of this radiation-dominated era in the cosmic microwave background. The patterns of hot and cold spots in the CMB are acoustic oscillations, sound waves in the primordial plasma. And those sound waves were driven by the gravitational effects of radiation. So when we look at the CMB, we're seeing direct evidence of gravity without mass shaping the universe at its earliest stages. But it goes even further back. In the first 10 to 43 seconds after the Big Bang, the Planck epoch quantum gravity effects dominated. Space-time itself was quantum, fluctuating and uncertain. In this regime, our usual concepts of space, time, matter, and energy break down. What does gravity even mean in such a state? What does mass mean? These are open questions. But many approaches to quantum gravity suggest that in the Planck epoch, space-time was fundamentally discrete. made of quantum bits of information, and what we call gravity emerged from the relationships between these bits. If that's true, then at the very beginning of the universe, there was no mass at all. There was only quantum information, evolving according to the laws of quantum gravity, eventually cooling and organizing itself into the space-time, matter, and energy we see today. The universe began without mass. Gravity existed first. Mass came later. This is a profound inversion of our usual understanding. We think of matter as primary and gravity as its consequence. But the history of the universe suggests the opposite. Gravity, or something like it, was there from the beginning, and matter emerged later as a particular organization of energy. And looking forward to the far future, something similar might happen. The universe is expanding, accelerating, driven by dark energy. As it expands, matter becomes more dilute. Eventually, in trillions upon trillions of years, stars will burn out, black holes will evaporate, and the universe will become a cold, nearly empty void. But it won't be truly empty. Dark energy will still be there, creating a gentle, repulsive gravity that continues to drive the expansion. The universe will approach a state called de Sitter space, an exponentially expanding spacetime with no matter, only the energy of the vacuum. In this far future, gravity will still exist, but mass will be gone, diluted to nothing by the vast expansion. The universe will return to a state where gravity exists without mass, just as it was in the beginning. Alpha and Omega, the beginning and the end. Both are states where gravity exists without mass, and the era where mass is important. The era we live in is just a temporary phase in between. You exist in this brief window of cosmic history where matter matters, where mass is important, where the distinction between massive and massless particles shapes the structure of reality. But this window is not the fundamental state of the universe. It's a phase, a temporary configuration in the eternal evolution of spacetime and energy. Understanding this puts your existence and all of human history in a profound context. We are creatures of matter living in a universe that is ultimately about energy. We experience gravity as the force of mass, but that's just a limited perspective. The fuller picture is that gravity is the geometry of spacetime, responding to energy in all its forms, and mass is just one particular manifestation of that energy. Now, before we move to our final sections, I want to address something that might be bothering you. With all this talk about gravity existing without mass, about mass being emergent and derivative, you might be wondering, why do we experience mass as so fundamental? Why does it feel so solid, so real, so primary? The answer is that evolution has shaped your perception to navigate the world at human scales, where mass is indeed the most important factor. You need to know whether a rock is heavy before you try to lift it. You need to know whether an animal is big and massive before you decide whether to hunt it or run from it. Your senses, your intuitions, your cognitive architecture, all of it is optimized for the world of everyday experience, where Newtonian physics is a good approximation and mass is a useful concept. But reality doesn't care about what's convenient for human cognition. At fundamental levels, at cosmological scales, in extreme conditions, the deeper truth emerges. Energy is fundamental. Spacetime is dynamic. Gravity is geometry, and mass is derived. It's like color. You perceive colors as fundamental properties of objects. The apple is red. The sky is blue. But color isn't a property of objects. It's a property of the light they reflect, and more fundamentally, it's a construction of your visual system, a way of encoding information about different wavelengths of electromagnetic radiation. Color feels real and fundamental because evolution made it feel that way. It's useful for survival, but it's not fundamental to physics. Mass is similar. It feels real and fundamental because that's useful for navigating the world. But at the deepest level of physics, it's a derived quantity, an emergent property of energy configurations in quantum fields. Recognizing this doesn't make mass less real in practical terms. The rock is still heavy. You still have inertia. The Earth still orbits the Sun. But it changes what these things mean. It reveals them as higher-level descriptions of something more basic. And this is true of so much of our experience. Temperature, pressure, sound, like these are all emergent, higher-level descriptions of something more fundamental happening at the atomic and subatomic scales. Even time and space themselves might be emergent, arising from something more primitive and more strange. Some approaches to quantum gravity suggest that spacetime is not fundamental, but emerges from quantum entanglement between more basic degrees of freedom. If that's true, then asking, can gravity exist without mass, is almost quaint. It's like asking whether a wave can exist without water, when in fact, both the wave and the water are emergent patterns in something more fundamental. This is the direction that physics is heading, deeper and deeper, finding that each level we thought was fundamental is actually emergent from something below it. And we're starting to glimpse what might be at the very bottom. Quantum information, mathematical structure, perhaps nothing more than pure abstraction made real through its own self-consistency. It's dizzying. It challenges every intuition. But it's also exhilarating because it means that reality is far richer and stranger than we imagined. The universe is not a clockwork mechanism. It's an ocean of possibility, with consciousness and matter and gravity and time, all emerging from the same underlying quantum substrate. You are part of this. You are a pattern in the quantum information structure of the universe, complex enough to process information, to be aware, to ask questions about your own nature. And in asking these questions, in trying to understand gravity and mass and energy, you're participating in the universe's exploration of itself. Now, I want to shift gears and talk about some of the cutting-edge research happening right now, because this isn't just history and philosophy. This is active, ongoing science, with new discoveries being made constantly. In 2021, a team of physicists at the University of Vienna, led by Marcus Aspelmeyer, successfully created what they call a quantum superposition of gravitational fields. They took a tiny particle and put it in a quantum superposition existing in two places at once, and showed that the gravitational field of the particle was also in superposition. This is significant because it's the first direct evidence that gravity behaves quantum mechanically at small scales. And it opens the door to testing other quantum properties of gravity, including how gravitational effects arise from energy and information rather than just from classical mass. There are also experiments underway to test something called the gravitational Aharonov bomb effect, which would show that the gravitational potential, not just the gravitational field, can have observable effects. This is directly related to the question of whether gravity is fundamentally about mass or about something more abstract. At CERN and other particle physics laboratories, physicists are studying the Higgs field with ever greater precision, trying to understand exactly how it gives particles mass and whether there might be additional fields or mechanisms involved. Every new detail about the Higgs reveals more about the relationship between mass and energy at the fundamental level. Cosmologists are analyzing data from telescopes like the James Webb Space Telescope, looking for signs of how dark energy has evolved over cosmic history. If dark energy is truly vacuum energy, and if it's variable, that could reveal new aspects of how massless energy curves spacetime. Gravitational wave astronomers are detecting more and more events, black hole mergers, neutron-star collisions, and each detection provides data about how gravity works in extreme conditions. They're looking for subtle effects that might reveal deviations from general relativity, hints of quantum gravity, or extra dimensions, or other exotic physics. All of this research is converging on a deeper understanding of gravity, mass, energy, and information. Within the next decade or two, we might have definitive experimental evidence for quantum gravity. We might detect signatures of extra dimensions or string theory. we might finally understand what dark energy really is. Or we might discover something completely unexpected, something that forces us to revise our entire framework for understanding physics. That's the exciting part. We're at the frontier. The map has blank spaces, and we're filling them in. And every time we explore a blank space, we find that it connects to others in unexpected ways. The question of gravity without mass turns out to connect to quantum mechanics, to cosmology, to information theory, to the nature of spacetime itself. Science is not a collection of isolated facts. It's a web of interconnected understanding, and when you pull on one thread, the whole web moves. We pulled on the thread of, can gravity exist without mass? And the whole tapestry of modern physics has shifted in response, revealing patterns we didn't see before. Now, as we start to move toward our conclusion, I want to talk about what all of this means for you personally. Not you as a physicist or a student, but you as a human being living in this universe, trying to make sense of your place in it. We've established that gravity doesn't require mass. We've seen that mass itself is emergent, arising from energy and field configurations. We've explored how the universe began and will end in states where mass is absent, but gravity remains. We've touched on how consciousness and observation might connect to the information theoretic foundations of spacetime. But what does any of this matter for your life? Here's what I think. Understanding the true nature of gravity and mass changes how you see yourself and your relationship to the universe. You are not a collection of solid, massive particles floating in empty space. You are a pattern of energy, a complex organization of quantum fields, generating spacetime curvature simply by existing. You are not separate from the universe. You are the universe, locally organized in a way that can think and feel and wonder. The gravitational field that you create, tiny though it is, extends forever. It falls off with distance, becoming weaker, but it never goes to zero. Your gravitational influence touches every other particle in the observable universe. You are connected to everything, and every other particle is connected to you. The gravity you feel is the cumulative effect of every massive object, every bit of energy, every quantum fluctuation in the universe. The Earth dominates, certainly, but the Moon contributes, and the Sun, and the galaxy, and distant superclusters of galaxies billions of light years away. You are held in place by the entire cosmos. This isn't metaphorical, it's literal. The curvature of spacetime at your location is determined by the energy distribution of the entire universe, past and present, because gravitational effects propagate at the speed of light and integrate over all of cosmic history. When you feel weight, when you feel the pull of gravity, you're feeling the shape of spacetime as determined by billions of years of cosmic evolution, by every star that ever burned, by every galaxy that ever formed. You are embedded in history. You are connected to everything that has ever happened. And your existence, your energy, your information content contributes to the spacetime geometry that will affect everything in the future light cone originating from your location. You matter, quite literally. Not because you have mass, but because you have energy. You process information. You participate in the universe's evolution. This is empowering. It means you're not insignificant. You're not a meaningless speck in an uncaring cosmos. You're an integral part of the cosmic structure, as essential as any star or galaxy, because every bit of energy contributes to the whole. It's also humbling. It means you're not separate or special. You're made of the same stuff as stars, governed by the same laws, subject to the same forces. The distinction between you and the rest of the universe is arbitrary, a matter of definition and convenience, not a fundamental feature of reality. Both things are true simultaneously. You are integral, and you are part of the whole. You matter, and you are matter. You have significance, and you are embedded in something infinitely larger than yourself. This is the paradox at the heart of existence, and understanding gravity, really understanding it, seeing how it arises from energy and information. Recognizing that mass is derivative helps resolve that paradox. You are significant because you are connected. Your meaning comes not from being separate, but from being part of a pattern. Now, there's one more aspect of this that I want to explore before we wrap up, and it's the most speculative, but also potentially the most profound. If gravity can exist without mass, if space-time can be curved by pure energy and information, then what about consciousness? What about thought, experience, awareness? These are information processing phenomena. Could they have gravitational effects? The direct answer, based on current physics, is yes, but unimaginably small. Your thoughts are encoded in electrochemical signals in your brain. Those signals have energy. That energy curves space-time, but the effect is so tiny that it's completely negligible by any practical measure. But let's think bigger. What if consciousness, what if information processing, plays a role in the universe that we don't yet understand? What if the act of observation, of extracting information from the quantum state of the universe, has subtle effects that accumulate over cosmic scales? This is the territory of speculation, but it's grounded in real physics. Quantum mechanics tells us that observation matters, that it affects the state of the system being observed. Information theory tells us that information processing is a physical process with thermodynamic consequences. Holographic principle tells us that information might be more fundamental than we thought. Put it all together, and you can start to wonder, might conscious observation play a role in shaping space-time? Might the universe need observers to fully exist, to resolve quantum superpositions into classical reality? This sounds mystical, and I'm not claiming it's definitely true, but it's a question that some physicists take seriously. John Wheeler, whom I mentioned earlier, proposed something he called the participatory universe, where observers are not just passive recipients of information, but active participants in bringing reality into being. The idea is that in the early universe, before conscious observers existed, the state of the universe was quantum, undefined, a superposition of possibilities. As the universe evolved and complexity emerged, eventually giving rise to conscious observers, those observers began to extract information, to make measurements, to collapse quantum superpositions. And in doing so, they retroactively defined the history of the universe. It's a wild idea. It requires quantum effects to persist across enormous scales, which is controversial. But it takes seriously the role of information and observation in quantum mechanics and extends it cosmologically. Whether or not Wheeler's specific idea is correct, the broader point stands. If the universe is fundamentally informational, if gravity emerges from information, then consciousness, as an information processing phenomenon, might be more central to physics than we've realized. You might not just be a pattern in the universe. You might be part of the process by which the universe defines itself. Again, this is speculative, but it's the kind of speculation that emerges naturally when you follow the logic of gravity can exist without mass all the way to its conclusions. You end up with a picture where energy, information, observation, and consciousness are all woven together in the fabric of reality. And that picture suggests that you, as a conscious observer, as an information processing system, as a localized concentration of energy and complexity, are not separate from the physics. You are the physics, looking at itself. Now, as we approach the end of this journey, I want to bring everything together and give you a framework for thinking about all of this. We started with a simple question: can gravity exist without mass? And the answer, definitively, is yes. We've seen multiple examples, from light creating gravity to gravitational waves, to vacuum energy, to theoretical constructs like Kugelblitz. We've traced this back to Einstein's field equations, which fundamentally relate space-time curvature to energy and momentum, not specifically to mass. But answering that question opened up deeper ones. If gravity doesn't require mass, then what is mass? And we found that mass is not fundamental but emergent, arising from the energy of quantum fields and the Higgs mechanism. At the deepest level, mass is a particular way that energy is organized, not a fundamental property of reality. This led us to quantum gravity and the holographic principle, where we discovered that space-time itself might be emergent, arising from quantum information. Gravity might not be a fundamental force, but an entropic effect, a consequence of how information is organized. We explored the cosmological implications, seeing how the universe began without mass, went through a phase where mass was important, and will eventually return to a massless state dominated by dark energy. Mass is a temporary feature of our cosmic epoch, not an eternal aspect of existence. We looked at the experimental frontier, at the research being done right now to test these ideas, to probe quantum gravity, to understand dark energy, and the Higgs field and gravitational waves. And we considered the philosophical and personal implications, how understanding gravity and mass changes your relationship to the universe, revealing you as an integral part of cosmic structure, connected to everything, participating in the information processing that might be the deepest nature of reality. The framework I want to leave you with is this: reality is layered. At the surface, at the level of everyday experience, mass seems fundamental, and gravity seems like a force between masses. This is Newton's layer, and it works perfectly well for most practical purposes. Deeper down is Einstein's layer, where we recognize that gravity is space-time curvature and mass is just one form of energy. Here, we can understand gravity without mass as a natural consequence of the field equations. Deeper still is the quantum layer, where particles are fields, fields are quantum, and everything is probabilistic and uncertain. Here, mass emerges from field interactions, and even space-time might be quantum. And perhaps deepest of all is the information layer, where reality is fundamentally about quantum information, and everything else, space-time, particles, forces, mass, energy, emerges from how that information is organized and processed. Each layer is real. Each layer is useful. But deeper layers are more fundamental, more complete, more explanatory of why the higher layers work the way they do. Your everyday experience of mass and gravity is valid. The rock is still heavy. The earth still pulls you down. But now you understand why. Because energy curves space-time. Because quantum fields interact to create mass. Because information organizes itself into patterns we call particles and forces. You see deeper. You understand more. And that understanding doesn't diminish reality. It enriches it. The universe becomes more wondrous, not less, when you understand how it works. So, can gravity exist without mass? Yes, absolutely. Definitively, yes. But more importantly, asking that question takes you on a journey through the deepest ideas in physics, from general relativity to quantum mechanics to information theory to cosmology. It challenges your assumptions. It expands your mind. It connects you to the fundamental nature of reality. And that's what science is really about. Not just answering questions, but using questions as vehicles for exploration, for pushing boundaries, for seeing further and deeper than anyone has seen before. You've been on that journey with me for these past few hours. If you've made it this far, you're part of a small group of people who care enough about understanding reality to invest serious time and mental effort. That's rare. That's valuable. That's how progress happens. People like you, willing to grapple with difficult ideas, to follow arguments to their conclusions, to let your mind be changed by evidence and logic. So before I wrap up, let me ask you one more time. Hit that subscribe button if you want more of this. Like this video if it changed how you think. And comment seriously. Drop a comment telling me what blew your mind, what you want to explore next, where you are, and what time it is. I read every comment. I want to hear from you. And tell me, has your understanding of gravity and mass changed? Do you see the universe differently now? Do you see yourself differently? Because that's the real goal here. Not just to convey information, but to transform understanding. To help you see reality as it truly is: strange, beautiful, interconnected, and far more amazing than common sense would suggest. We live in an age where we can probe the fundamental nature of reality. We have the mathematics, the experiments, the observational tools to ask questions that would have seemed impossibly deep just generations ago. Can gravity exist without mass? What is the nature of spacetime? How does consciousness relate to physical law? What happened at the Big Bang? What is reality fundamentally made of? These are questions humans have wondered about for millennia, but we're the first generation with any hope of actually answering them. And we're making progress. Genuine, measurable, scientific progress. Gravitational waves detected. Higgs boson found. Cosmic acceleration measured. Quantum entanglement verified. Each of these is a piece of the puzzle, a clue to the deeper nature of things. And the picture emerging is extraordinary. Reality is not what it seems. Space and time are flexible. Mass is emergent. Gravity is geometry. Information is fundamental. Consciousness might be woven into the fabric of physics. This is the universe you live in. Not a clockwork cosmos of rigid matter obeying simple laws, but a quantum hologram of energy and information, giving rise to space and time and matter and mind through its own complex self-organization. You are not in the universe. You are of the universe, made by it, part of it, expressing it. And when you ask questions about gravity and mass, when you probe the foundations of physics, you're not investigating something external. You're investigating yourself, your own nature, the nature of the awareness that's asking the questions. Science becomes meditation, becomes philosophy, becomes science again. It's all one inquiry, one journey into the nature of what is. So I'll end with this. Gravity can exist without mass because reality is more fluid, more fundamental, more deeply interconnected than our intuitions suggest. Mass is a convenient shorthand, a useful concept, but not a fundamental property. Energy is deeper. Information is deeper still. And beneath it all might be something we don't even have words for yet, some mathematical structure or logical necessity that gives rise to existence itself. We don't know the final answer. We might never know. But we can keep asking, keep exploring, keep pushing deeper. And you can be part of that. By watching videos like this, by reading, by thinking, by questioning your assumptions, and following arguments wherever they lead, you participate in humanity's grand project of understanding reality. That matters. You matter. Not because you have mass, but because you have energy, because you process information, because you're part of the pattern. Thank you for taking this journey with me. Thank you for caring enough about truth to invest hours of your time. Thank you for being curious, for being open-minded, for being willing to have your understanding challenged and expanded. The universe is vast and strange and beautiful, and now you understand it just a little bit better. Keep questioning, keep exploring, keep wondering, and remember, gravity doesn't need mass. It needs energy, it needs information, it needs patterns in space-time. It needs you. Until next time, keep looking up, keep thinking deep, and keep asking the questions that matter. This has been your deep dive into whether gravity can exist without mass. The answer is yes. But more importantly, the question is an invitation to understand, to explore, to participate in the greatest adventure humanity has ever undertaken. The quest to understand the nature of reality itself. You're part of that quest now. Welcome aboard.